So our next speaker has joined, Dr. Manikandan S. from SRM University. I would like to call Raisa Rashid, Professor Raisa Rashid, to introduce the speaker.
So our next section is being handled by Dr. S. Manikandan. Dr. S. Manikandan is Assistant Professor in the Department of Mechanical Engineering at SRM Institute of Science and Technology, Chennai. He earned his PhD in Energy Engineering from IIT Delhi in 2017 under Professor S.C. Kaushik and received the distinction in Doctoral Research Award from IIT Delhi. His research focuses on electronic thermal management, bifacial photovoltaic systems, solar PV waste management, daytime radiative cooling, and thermoelectric devices. He was awarded the Bhavan Fellowship in 2016 by the Indo-US Science and Technology Forum. He has contributed significantly to academia with 5 Indian patents, 35 international journal publications, 3 book chapters, and 1 book on thermoelectric energy conversion. He is a life member of the Solar Energy Society of India. He currently leads 500 projects supported by Bureau of Indian Standards, ISRO, and MSME. Dr. Manikandan serves as the Department Coordinator of the Center of Excellence for Electronic Cooling and CFD Simulation at SRM ISD, established in collaboration with Intel Corporation USA. So I welcome you, sir, to this session. No, sir, you are not audible.
Hello. Am I audible now?
Yes, sir, you are audible.
Yeah, okay. I'm turning off the video for the bandwidth. I'll share the screen and then I'll start the presentation. Is my screen visible?
Yes, sir.
Yeah, okay. Yeah. I hope the screen is visible now, right?
Yes, sir, it is visible.
Yeah, okay. Yeah. Actually, I'm on full screen mode. So like if I wanted to ask, please interrupt and then talk. Okay. That would be better because I could not able to see people in the meeting. Yeah. Thank you. Good evening. I think it was a little late also in the night and most of the people will be having their dinner. So I'll take some of your time to explain some very interesting topic which is related to the sustainability development and also carbon neutrality. That was the theme for this at LFDP. Thank you for inviting me again. Yeah, we will dive into the topic. Thanks for the introduction too. Today we will learn about radiative cooling potential and applications in India. Apart from this, we will also learn what are the alternative cooling technologies we may have and how it can be utilized, and some technologies and some case studies I'll be presenting it here today. So part of my research, I'll introduce about my research group, and then we will talk about the India Cooling Action Plan. It was a government initiative. Then we will look into the conventional cooling systems, and then we will dive into the radiative cooling topic. We will discuss about that in great detail. Then what are the research we have done at SRMIST on the topic of radiative cooling, and what are the potential we may have for further research in the radiative cooling, and some case studies also I'll present today. So about our research group, we have a lab, Energy Conversion Technologies Research Lab. We mostly work in sustainable energy solutions, mainly in the electronic thermal management, thermoelectric energy conversion systems, radiative cooling, and solar photovoltaics, bifacial as well as the agri-photovoltaics, solar PV waste management also. These are the topics of the research actually we do at our research group, and some of the PhD students will also be working on this. We extensively work on the applications, and we do collaborations with the industries as well as other academia, and get some funded projects from the industries as well as the government funded agencies, and then we will try to solve the problems which are related to the sustainable energy systems and solutions. So first we'll talk about India Cooling Action Plan. Then it was action plan which was devised by the Government of India, and they have published a report in 2019 saying that refrigeration and air conditioning is one of the major consumer of electricity. So electricity is consumed in all other sectors too, but refrigeration previously an luxury, but now it is becoming a part of our life. It is a basic necessity, right? So that people will be, our occupant will stay healthy. Also, they can work peacefully and stay peacefully and stay indoors. And it is consuming a major amount of electricity, and the refrigeration and air conditioning demand may also increase manifold in the future. And they have projected the refrigeration demand to be around 1,000 million metric tons, 1,000 million tons of refrigeration, 1,000 million tons of refrigeration, maybe 2037 to 38 in that period. And the major share which will be coming from the space cooling of the buildings, and the 10% may be contributed by the refrigeration, and partly by transport air conditioning, and a very minuscule amount for the cold chain. So, but when you look into the emissions which are coming out from the refrigeration and air conditioning systems, 90% which will be caused only because of the energy consumption, not related to the ozone depletion because of the refrigerants. So what government decided, like, okay, what we can do further to curtail these emissions, or whether we can work on alternative refrigeration technologies so that this demand can be reduced and energy efficient systems can be developed, so that it will contribute to this sustainable development. So they have provided, they have come up with some 5 objectives. First one is recognize the cooling and related area as the thrust area. Now, semiconductor is becoming a thrust area. Similarly, cooling and the related areas as the thrust area for the research. And they should support more research and development and new technologies and innovations in this related field, cooling and other related areas. And second objective is to reduction of cooling demand by 20 to 25%. Okay, Reduction of cooling demand means we should not think that we have to reduce
It's
the cooling. It is not the reduction of the cooling or not getting the access of the cooling, but reducing the demand, okay, maybe by sustainable buildings or so. And the reduction of refrigerant demand by 25% to 30% by the year 2037 to 38, which means like we have to from the refrigerant based technologies to non-refrigerant based technologies or alternative refrigerant based technology, so that the refrigerant leakage or any other things may not harm the environment, because actually the refrigerants may cause the have a huge potential of global warming as well as for the ozone depletion. And the fourth one is the reduction of cooling energy requirements by 25 to 40%. And also fifth objective is to train the sector with 0.1 million technicians, so that whatever the huge demand in this sector can be easily met through the skill training. So now we will look into, like, these are the objectives. So now we will look into what are the conventional technologies we have and how it works, and what are the alternative cooling technologies we may have, and what are the advantages about it, and which one we can choose it, and why we can choose that. Okay, so we will look into the conventional VCR and VAR system. VCR means vapor compression refrigeration systems, and VAR means vapor absorption refrigeration systems. So this is the cycle diagram of a vapor compression refrigeration systems. It is most common, which is used in our household refrigerator, air conditioners, everywhere, and also in the case of single household or to any shopping complexes, everywhere they'll be using the similar kind of systems, but the size may vary, the tonnage may vary, the tons of refrigerations may vary. And how exactly this works? We have an evaporator here. We have an evaporator here. Evaporator, the name suggests that the evaporation will happen here. And we have a throttle valve, and we have a condenser, and we have a compressor. So what exactly it happens is, and the cycle where exactly the refrigerant will move. The refrigerant will move from the evaporator to the compressor, compressor to the condenser, and the condenser to the throttle valve, and throttle valve to the evaporator, and it will be cycled again and again. So in the case of evaporator, the liquid refrigerant which evaporates, so from liquid state it will go to vapor state, and that vapor will be compressed to high pressure, and then that vapor will be condensed, and that condensed high pressure vapor will be throttled, because we need a low pressure liquid vapor here, liquid vapor refrigerant, so that this, when the low pressure liquid vapor refrigerant comes into contact with the some object, it is to be cooled, so it absorbs the heat and it will evaporate. So when it absorbs the heat from the environment, it will cool down. So the evaporator region is the region where exactly it is cold, and the condenser region, it will be rejecting the heat which is being absorbed by the evaporator. So it is a heat transfer device rather than we say that heat conversion device. It transfers the heat which is being absorbed by the evaporator, and it rejects through the condenser. Okay, and only the active power consuming device is the compressor here. So it consumes the electricity, and it pumps the refrigerant from the evaporator to the condenser, and it is also very much required, so that when the refrigerant at high pressure comes into contact with the atmosphere, that is a sink which is having lower temperature. So when it comes into, when the high pressure refrigerant high temperature refrigerant comes into contact with the ambient, which is at lower than the saturation temperature, then it will definitely condense. So it will be again converted into the vapor to the liquid. And we can convert that liquid to vapor again. So this energy conversion or the energy transfer process will continue. So I'll skip this PS diagram. And this is the vapor compression refrigeration systems and vapor absorption refrigeration systems comparative diagram. In the case of vapor compression refrigeration systems, we are using a compressor. And in the case of vapor absorption systems, instead of having a compressor, we will be using a thermocompressor. Okay, since compressor is the only active energy consuming device in the case of vapor compression refrigeration systems, so we'll be utilizing thermocompressor technique. So in that case, the refrigerant, the other equipments remain the same. Like we have a condenser here, and we will also have a condenser here. We'll have an evaporator here, and we'll have an evaporator here, and we'll have an expansion valve or throttle valve. That will also remain the same. But instead of a compressor, we'll be using this generator and absorber, and again a pump. So these systems will act as a thermocompressor. Okay, compressor will consume more amount of energy, and it will consume electrical energy. In the case of thermocompressor, we have to supply the heat and a little amount of electricity so that we will get the same operations which is done by this electrical compressor. Okay, we have a generator. Like in the case of here we can see that the vapor will come out of the evaporator. That will be absorbed by the liquid absorbent. And that liquid absorbent, since it is a liquid, we can use a pump to pump it to the generator. And the generator, the name suggests that it generates. So it absorbs, it takes some amount of heat and generates the refrigerant vapor. Go to the condenser, and the condenser, it condenses. This vapor will condense, and then it will come down and it will come to the evaporator as a low pressure liquid. Now, here in the case of absorber, we will be pumping the liquid, and in the case of generator, getting the vapor, refrigerant vapor, and there will be absorbing liquid also. The absorbent will also there. That absorbent will come down to the absorber again, and this cycle will continue. And whenever we are supplying the heat, we can generate the refrigerant vapor. So this what we call it is the thermocompressor. We can operate this in the sustainably. Instead of supplying the heat through any other means, we can supply the heat through solar energy. So if we supply the heat through the solar energy, we can easily generate the refrigerant vapor, and that can be sent to the and then to the expansion valve and the evaporator, and this cycle will continue. So here there will be absorber cycle, and here it will be a refrigerant cycle. So here the refrigerant and absorber will be going, and we call this as a rich solution, and this is a weak solution. The solution which is having the refrigerant as well as the absorber, we call it as the rich solution, meaning that rich in refrigerant. And then once refrigerant is generated, refrigerant vapor is generated, and that refrigerant vapor will go to the condenser, so that the solution will become weak in refrigerant. So we call it as a weak solution. And again, it has a high affinity to absorb more amount of refrigerant vapor, so it will get absorbed, and then this cycle will also continue. So here also we can generate the cooling without the use of very harmful refrigerants, and also we can utilize the solar energy to produce the refrigerant vapor. So, and very little amount of energy, electric energy is being consumed. That is for the pump. So this may be one of the sustainable solutions, and this kind of solutions are already in place in some of the shopping complexes and malls. So there are different pairs, refrigerant and absorber pair is also there. Say in the case of ammonia and water, ammonia will be acting as the refrigerant, and there are other solutions also, liquid water and the lithium bromide. And in the case of water and the lithium bromide, water will act as a refrigerant, and the lithium bromide will act as an absorber. So this ammonia, it can go below ambient temperatures, so below 0 degrees also. So it can be used for refrigeration purposes. And water, lithium bromide, they will be using it for air conditioning purposes, because the water as a refrigerant, it cannot go beyond 4 degree or negative 4 degrees, otherwise it will freeze. So these are some of the conventionally available refrigeration systems, which are VCR and VAR systems. Now we will look into some of the techniques. The first one is we can say that thermoelectric cooling. Thermoelectric cooling, it says, what are the systems actually we have seen here? It uses some refrigerant. Yes. Suppose if you wanted to use get some cooling without any refrigerant, then we can go for electronic cooling or electronic systems. That we call it as the thermoelectric cooling, in which there is no refrigerants, but the electrons, because of the movement of this charged particles, that electrons or holes, we can say, there will be some amount of energy which will be transferred from the hot region or from the cold region to the hot region. Okay, but remember, we have to supply some amount of electricity for this. So in this case, how exactly this will work? Say, take an example. In the case of a refrigeration system, thermoelectric refrigeration systems or Peltier-based refrigeration systems, we'll be having two dissimilar materials. Maybe in our case, we'll take a semiconductor materials, N-type as well as the P-type. And N-type will have more number of free electrons, and P-types will have more number of holes, and which are connected electrically in series, thermally in parallel. Why electrically in series? Because we have electrical connections which will be running in series. And thermally in parallel, because we have connected these two legs between these two heat reservoirs. One is a cold reservoir and a hot reservoir. So there are parallel paths for the heat transfer. So we can say that thermally in parallel and electrically in series. So take an example of this junction alone. So we told that N-type will have more number of electrons, and this is a metal. So to conduct or to form a junction. So in the case of metals, we can see that there are more number of free electrons which will be available. Even at the room temperature, we can find the electrons which are freely available. And also we can say that in the case of metals, the conduction band and the valency band are overlapped. So its electronic or the energy level, which will be like this. So this is the metal, maybe copper, and this may be the N-type material. And in the case of N-type material, there is a Fermi function, that is a Fermi level. That Fermi level will be near to the conduction band and to the, this is the valency band. So in the case of a metal, an electron will move from the Fermi level to the conduction band, so that it will move from here to here, right? Why it will move? Because there is a potential difference. If there is a potential difference, the electron have to flow. If an electron have to flow from the Fermi level to the conduction band, meaning that it is moving from the lower energy state to the higher energy state, it have to absorb some amount of energy from the ambient. So when it absorbs some amount of energy from the ambient will get cooled, or ambient's energy will decrease. So which means it is getting cooled. So this junction will get cooled. Suppose, say, what happens? The energy, the electron, which is in the N-type material, and which will again come, it have to transfer to the copper material. So when the electron jump from the higher energy state to the lower energy state, it have to release some amount of energy. So energy is added here at this junction, and energy is being absorbed at this junction. So where exactly the energy is absorbed, the space will become cool, and where exactly the energy is being released, it will become hot. So this is also an alternative cooling technology. We can cool as well as heat any object or any systems or any devices or any space without any use of refrigerant. And the role of, there is no refrigerant used here, but the only problem with this is like it consumes an electricity. And the efficiencies of this kind of devices, which will be much lesser when compared to vapor compression refrigeration systems. So it is currently being used in some very small systems, like very small ice cube makers or chillers, and small water coolers, probably. Okay, not for space and building cooling applications. But there are people who are doing research on this too, and we are also doing some research on this as well. This one is an alternative cooling technology. This can be operated by using PV also. So instead of supplying the grid electricity, you can apply the PV. So this will be an alternate option which will be sustainable. Okay, but there is a problem. We cannot be used it for higher power levels. Okay, now we will look into one more technology which doesn't use refrigeration and doesn't consume any power, but it will cool. It has the capacity to cool. Okay, and capacity or to subambient temperatures. Okay, now as per the laws of thermodynamics, cooling is a spontaneous process and refrigeration is not. Okay, because anything which can be cooled to the ambient temperatures, but if you wanted to go beyond subambient temperatures, we call it refrigerations. Say refrigeration means negative temperatures too, but what I'm saying is like beyond or below subambient temperatures, it violates the second law of thermodynamics, correct? Because energy cannot be transferred from lower energy state to the higher energy state without any external energy being supplied to it. Okay, but the systems like we will be looking next is a kind of a system which will obey the second law of thermodynamics, but it has the capacity to cool below subambient temperatures without the electricity consumption and also without the need of any refrigerants. Okay, isn't it cool? So how it can be done, or how it is being done? Okay, suppose say you have an object which is at some temperature, okay, TR, and you are keeping that object on a clear sky day or the night in your house rooftop, okay, which is maybe at 100 degrees Celsius. Assume that you have a hot iron block or a potato which is boiled and you are keeping it in in your balcony, not in the balcony. Balcony will be too shaded or view factor may not be there. But if you are keeping it in the roof and you allow that to cool overnight, okay, what are the possible options which may happen? The temperature will definitely going to decrease. Yes, the temperature of this object is going to decrease. That is for sure. But how much it may decrease, we don't know. And what are the factors which will influence in that cooling, we will explain one by one. Okay. And it will cool to that object which is at 100 degrees Celsius, which may cool to the ambient temperature. Yes, it is obviously, it can cool to ambient temperatures. In this, there are three modes of heat transfer will be there. Convection to the ambient will happen, and evaporation and radiation will also happen to the near objects or to the sky, right? So this will cool to the ambient temperature by convection, evaporation, and as well as the radiation, right? Now, will it has the potential to cool below ambient temperatures? Yes, there is a possibility. It can cool to TW or the wet bulb temperature through evaporation and radiation. But remember, once it go below ambient temperatures, there will be some amount of heat which will be absorbed by this object from the ambient, because the ambient is at higher temperatures. So convective heating will happen, evaporative and radiative cooling will happen. Okay. Now, assume there is all the present in that object is being dried out. Okay. Now what happens? Will it has the potential to cool? Yes, there is a possibility. And that happens only by radiative cooling. Okay. Radiative cooling and convective heating. Why there is a convective heating? Because that object is below ambient temperature and that ambient is at higher temperature. So flow from the higher temperature to the lower temperature. So thereby heating this object, trying to heat this object, and much higher than the convective heating potential, obviously the object is going to cool down further. Okay. Now, till what temperature this has the potential to cool down? Will it go to 0 degrees Celsius, or will it go to -5 degrees Celsius, or it may go to -10, 20, -70, -80? We don't know. And again, that depends upon, and that will cool to some fixed temperature that, okay. So it will cool to a temperature like of the sky. Okay. So it will cool up to the sky temperature. It has the potential to cool till the sky temperature. Okay. Now, how exactly this cooling will happen? Because cooling, as per the Stephen Boltzmann law, cooling can assuming that this body is a black body or a body with some surface emissivity. So we can say that emissive power will be proportional to or equal to emissivity into sigma, that is Stephen Boltzmann constant, and F r to the sky, that is the view factor between this body to the sky, and fourth power of the temperature of that body to the fourth power of the temperature of the sky. Okay. And we don't know what is the sky temperature, and the sky temperature will be different in different conditions, sky condition we would say. Okay. But nevertheless, of the sky conditions, the sky temperature will be lower or equal to the ambient. Okay. If it is an overcast sky, then we can say that it will be, or the very humid conditions, we can say that sky temperature may be equivalent to the ambient temperatures. But if it is the sky is or the atmosphere is dry and it is open, then on that case we can say that the sky temperature will be much lower than the ambient temperatures. Okay. So now if there is a potential, that is Tr minus of T sky is huge, then there will be heat will also be transferred from this body to the sky. Now we have two factors, epsilon of the body and also the view factor of the body to the sky. So the view factor of the body to the sky, meaning that like the sky have to be visible for that body. If that body is not visible to the sky, then definitely it may not transfer the heat. And epsilon is the here. Any queries? Okay. So
No, sir.
yeah, okay. Then please do mute.
അതുകൊണ്ട് നമ്മൾ കേൾക്കുക.
Yeah. And this epsilon r is the emissivity of the body. The epsilon r and what should be the T sky? These two things decides the radiative cooling, how much amount of heat which can be transferred from the body to the sky. Okay. Now we will look into what are the factors which affects the epsilon r and what are the factors which will be affecting the T sky, and how we can evaluate what will be the radiative cooling potential. Okay. Yes, you can see that it doesn't require, like say you are keeping an object, there is no refrigerant, and you are not supplying any electricity or nothing, but it is cooling down below the ambient temperatures. Yes, and that cooling can be utilized for building cooling applications or water generation applications and for soil cooling applications, varieties. Okay, n number of applications we can use it. Okay, so this is one of the sustainable solutions. Now we are saying that it is a very good solutions which doesn't use refrigeration and doesn't use electricity. Now, whether do we have potential or not, that we have to find out. In which locations we do have the potential, which location we do not have the potential, and which seasons it will have the potential, which season we not have the potential, whether all the objects with irrespective of the emissivity have the potential, we have to check. Okay, we'll study about that. So radiative cooling. See, since we are talking about the sky temperature, sky is not a solid body or a fluid. So, but how we can say that the sky does have a temperature? So it is a fictitious temperature, not exactly the actual temperature of the sky, but there will be some amount of radiation, long wave radiation, which will be coming or emitted from the sky, or it is away in that space. So what may be the equivalent temperature as per the Planck's law? That temperature we assume that as the sky temperature. Okay, the sky is not a solid body, but we can have a fictitious temperature based on the wave radiation which will be emitted by the sky. Okay, so that is what we call it as the sky temperature. And what may be the temperatures of the sky? It depends upon the clear and the dry night. The temperature may go to -60 degrees Celsius too. And clear night, it can go to -20 to -30 degrees Celsius. Overcast sky, meaning that the sky is fully cloudy, or the clearness index will be less than 0.3. In that cases, like it may be +5 degrees Celsius too, but nevertheless it will be slightly lesser or equivalent to the ambient temperatures. So if we have, or like if the atmosphere is dry and clear, we can utilize the coldness of the sky to cool the objects. Okay, so the same formula which I have mentioned previously, so I'll be putting it again. So you can substitute these values and you can find out whether do we have a potential or not. And it comes out to be, yes, we do have a potential. Now, whether this concept is new or old, this concept people have used even in the 16th to 17th centuries in India for cooling of buildings. Okay, and this oftenly termed as nocturnal cooling, meaning that nighttime cooling. This was an AI-generated image, so I asked Gemini to generate an image for the nocturnal cooling, and it created an image. It was again a very fantastic image, like depicting the actual things which happened in India, maybe in the 16th to 17th century. Okay, so you can see that the people like making ice when the sky is clear, and that too at some high altitude region. And you can see that there will be slight amount of formation of ice. Actually, like this was one of the technique. Actually, earlier the kings used to cool their buildings by producing ice during the night time, and they can use it or they can store it, and then they will be using it during this in the daytime. Caution, there may not, this is again an AI image, so this much huge ice cannot be made, but yes, sheets of ice can be made, but that can be combined together. Yes, then you can make a bigger sheets of ice. Okay, nevertheless, the concept remains the same. They will utilize the coldness of the sky to generate the ice, and then we can utilize it on some other days, store it in some other days, and we can utilize it for cooling the space. This happened. Okay. Now, whether we have a potential only to cool during the night, now there comes the research. Okay. This, it can be done even at the night time. Today also, even if the sky is dry, the atmosphere is dry and the sky is clear, you keep a 1 liter of water or something on a shallow pan. Okay. Then you can absorb that the temperature. You may not get ice at Chennai or in Kollam or some regions, but definitely you can absorb the temperature of that water which are kept in the roof, maybe lower than the ambient temperatures. Okay, so that will be caused only because of the radiative cooling. Okay, not by any other means. Okay. Now there are now then people have worked on the emissivity part of the material. Like, since we have told about, there are this view factor as well as this emissivity, and this T sky we do not have any control on. FR sky, that is the view factor, that we have to keep it open to the sky so that that view for this object, which will not be obstructed by any other buildings or the trees or anything, so that heat can be easily transferred from that body to the sky. And then what the people have done is they have done the research mostly on the emissivity of the material. So what can be the emissivity of the material? We can coat that material onto any surface, then we can get maximum cooling. Okay, we will also talk about some of the materials used for this. Okay.
Excuse me, sir.
Yeah, please.
May I ask a doubt?
Yeah, please.
Okay. You have mentioned that the water can cool when we are placed outside the rooftop or some open places. Is it possible in summer seasons can we cool the water in the open places?
No, like, is it possible?
To cool the water during the summer seasons, because in the summer seasons it's the temperature is, the outside temperature is very high, right?
Yes.
So
Yeah,
actually,
like,
I don't
we can-
understand the cooling effect.
Yeah. Like, see, the cooling will be happening because of the sky temperatures. Okay. And remember here, if we are, the atmospheric temperature will be much higher. Remember, the atmospheric temperature will be much higher. And
During the summer season.
even
right?
if, correct. And even if you are getting the radiative cooling potential, more potential, assume that this atmosphere is dry and the sky is clear, then we have more potential. But again, convective heating will also be contributed, and that will also be more. Okay, we will come to the, actually I have an energy balance also. From there, you can easily understand this. Nevertheless,
Okay.
irrespective of the summer or winter, the sky based on the sky temperatures, the object has the potential to cool. Remember, the atmospheric humidity will definitely, or the moisture content in the atmosphere definitely decrease the radiative cooling effect. Okay, in the case of summers, humidity. Okay, so that is also one of the reasons, actually, like in the case of summers, we may not have much good potential for the radiative cooling, because we have already made a map, and based on that only I'm making these conclusions. But the energy, from the energy balance, you can easily identify this. Okay, and even after that energy balances, if you have more doubts, please do ask. We will explain further. Yeah.
Okay, thank you very much, sir. Okay, thank you.
Yeah. Okay. And forecast, the potential will be lower, and in the case of clear sky, the potential will be higher. Why? Because, like, more the path for the heat transfer because there is no cloud cover. So this object will easily see the sky. So there will be more amount of cooling. We can easily get it. Okay. This will be a factor which will be influencing in the case of cloud cover. Okay. Now, these are the basics which are constituents of the atmosphere, like what will be the temperature, pressure, and density. I think we'll skip this. And this also I'll skip. We can come directly here. Okay. And this one is the energy, and this is the wavelength. This will be plotted for a body which is at the temperature of 294 or like 21 degrees Celsius or 20 degrees Celsius. Okay. So if you plot this Planck, this is a Planck's distribution law, and this is drawn by the Planck's distribution law, this one, top one. So if you plot that Planck's distribution law, you can say that, or you can find that the maximum amount of radiation which will be emitted in the 8 to 13 micrometers, or we can see that the peak will be around 9 or 10 micrometers. Okay. This wavelength accounts for the infrared radiation, meaning that the body, irrespective of the temperature, which will emit some amount of radiation, and depending upon the temperatures, where exactly the maximum peak, that will be decided. So if it is a body of 6000 Kelvin, that is a sun, it will have the peak in the visible spectrum. And if it is a body which is having lower temperatures, then it will be having the peak in the infrared spectrum. Okay. So if you find a plot of black body like Planck's distribution law, as per the Planck's energy distribution, spectral emissive power based on the Planck's distribution law, you can find that maximum or the peak will be in the infrared, okay, IR region. And this is the emissivity of the body or the emissive power of the body. But now if you look into the atmospheric emissivity, okay, now if you look into the atmospheric emissivity, which are given in the second line and the third line, you can see a sudden dip in the atmospheric emissivity. Okay. Why there is an atmospheric emissivity? There is a dip in the atmospheric emissivity because at this region, the atmosphere, what exactly it means is the atmosphere will not absorb anything in this region. Any radiation, it will not be absorbed in this region. Meaning that the atmosphere is open for energy transfer. And this region, we call it as the atmospheric window. Okay. This is the natural phenomena. The God have designed the earth in such a way that, or the atmosphere in such a way that the radiation will not be absorbed by the atmosphere within this region, or like absorptance will be there, but that too very minimal. Okay. Now look into this, and that this region 8 to 13 micrometer, we call it as the atmospheric window. 8 micrometer to 13 micrometer, the atmosphere will not absorb, or atmosphere will absorb very less amount of radiation, and the radiation in the sense IR radiation. Okay. Now atmosphere will not atmosphere will absorb less, and also the body will emit more. Okay. So there are two things: atmosphere will absorb less, but the body will emit more. So now here, that is the potential actually we have. So more the emittance, the more the emissive power of the body, absorb very less. So more amount of radiation which can escape from the atmosphere to the sky. Okay. So this window, we call it as the atmospheric window. Okay. Now you can see that various ranges of wavelength, what are the constituents which will be present in the atmosphere which will contribute to the absorption. Okay. At 15 micrometer, maybe over here, CO2 absorption will be more, meaning that the CO2 which is present in the atmosphere, it will absorb. That is one of the reasons actually people say that we wanted to reduce the carbon dioxide emission. If the carbon dioxide which is present in the atmosphere, it will absorb the radiation which is emitted in the 15 micrometer IR spectrum. That will also contribute to the heating. Okay. Now 6.3 micrometer CO2 absorption, there is no absorption, but water absorption which will be high. Water vapor, if it is present in the atmosphere, then it will be absorbing at 6.3 micrometer. Ozone absorption, no. But around 9.6 here, if ozone is present in the atmosphere, it will absorb more. Okay, here. So that is why it is mentioned approximately 80% at 9.6 micrometer, which will be absorbed by the ozone. But there is weaker absorption by the water or the water vapor which is present in the atmosphere. Okay. And in the 8 to 13 micrometer window, CO2 will also be present, but absorption will be minimal, and water absorption will be moderate, and the ozone region will be moderate. Or moderate means like only in this region, or 9.6 only we will be having the peak for the ozone. Otherwise, there will be moderate amount of absorption. Okay, or minimum amount of absorption we can say. And in the greater than 20 micrometer, water vapor absorption will be there. Or in if the atmosphere has some more amount of water vapor, it will absorb or it will trap the heat. Okay, now what exactly this says? The object, if it is emitting energy in this 8 to 13 micrometers, it has the potential to escape from the the radiation which will be emitted can be easily escaped from the atmosphere without being trapped in the atmosphere. So if it is not being trapped in the atmosphere, it can easily cool because it is exchanging the heat to the sky, which is also at very low temperature. So this region, we wanted to maximize the emissivity of the body. Okay, so the body has the spectral emissive power is higher, but we wanted to maximize the emission from the body within this window. Okay, how we can maximize it? We can maximize or we can improve the emissivity of the body within this 8 to 13 micrometers. So if a body have a higher emittance only in this region, 8 to 13 micrometer, it can exchange the heat to the sky without being absorbed by the atmosphere. So its temperature can be decreased. Okay. So that is all about the atmospheric window. Now we will look into like whether this object, say to be cooled, is placed horizontally will give more cooling, or at 90 degree it will give more cooling, or what may be the influence of presence of the water vapor in the atmosphere, will that affect the cooling or not? So we said very less amount of radiation will be being absorbed by the atmosphere which is present within this 8 to 13 micrometer. Whether only in the atmospheric window we are concerned about now. So what may be the angular dependence of the atmospheric window? Suppose an object which is kept horizontally on the flat surface, then we call it as 0, which is easily visible to the sky. So more amount of radiation can be emitted, right? But if suppose if you are keeping it 90 degree, it will be visible to the half of the sky. Okay, so the absorption will be more in the by the atmosphere because it have to, the radiation have to travel more the distance. Okay, now what happens if you have more amount of water vapor in the atmosphere? So you can see that 1.5 centimeter of H2O, 3 centimeter of H2O, and 6 centimeter of H2O. What exactly this is what we call water column. Okay, water column means like suppose say if you have a small water column of 1 centimeter, and if you take the condense the water vapor content present in the atmosphere, and how much is the condensate we will be getting it, and that what we call it as a water column. Okay, so suppose say 1.5 centimeter of H2O means 3 centimeter of H2O, 3 centimeter of H2O, and 6 centimeter of H2O. What exactly this is what we call it as a water column. Okay, so less amount of water vapor present in the atmosphere. If lesser amount of water is, the atmospheric window will be too much deeper, meaning that no absorption will be there, or the minimum absorption will be there. Okay. But suppose say if you have more amount of water vapor in the atmosphere, then the water vapor itself absorbs some amount of heat radiation. Okay. If water vapor absorbs some amount of heat radiation, meaning that that heat will be trapped by the water vapor and it will not be escaping out to the sky. So lesser amount of radiation exchange. So lesser the amount of radiation exchange, lesser the cooling effect we will be getting it. So this is one of the reasons actually in the case of summer or the regions with high humidity may not have very good potential. Okay, this is one reason. Okay. Now, the same image which I am plotting it again. This is the Planck's law and the spectral radiance of the black body at 300, that is at 27 degrees Celsius. And if you look into the energy distribution, so 5% or like around 2% or 1.5%, it will be in the 5 micrometers, and approximately 35% of energy which will be emitted in the atmospheric window. Okay, so if we can make a coating that will have higher emissivities in 8 to 13 micrometers or 8 to 20 micrometers, then we can maximize the amount of radiation to escape out of the atmosphere from the body. Okay, then it means we can easily cool the body to a lower temperature or to the sky temperature. Okay, without being absorbed by any other, assuming that the atmosphere is dry. Okay. Now we look into what material or what kind of surface emissivity the material should possess to have very good cooling, to provide a good amount of cooling. Okay, so we can see that white paint. So this is alpha is the absorptance at the solar region, and epsilon IR means the emissivity. Okay, alpha equal to IR or alpha lambda equal to epsilon lambda as per the Kirchhoff's law. It means that alpha lambda cannot be equal to epsilon or like epsilon lambda 2. Okay, so we can have different absorptivities at the solar region and different absorptivities at the IR regions also. So for a white paint, emissivities at the IR region will be higher, but absorptance at the solar region should be lower. Why? If for the daytime radiative cooling, okay, in the case of nighttime, there will not be any solar radiation. Yeah. So in the case of nighttime, there will be no solar radiation also. So white paint may work good in the nighttime, but for a good radiative cooling material, it should have very low solar absorptance and higher IR emittance. Okay. So there are materials we can maybe I have shown it or not, I'm not sure, like otherwise it can be. So this is one factor. This is the another factor, very important factor that will be influencing the radiative cooling. Okay. So this one we can say this is one of the radiative cooling material that in the atmospheric window which will have very good amount of emittance, a very high reflectivity in the radiation solar spectrum, which means even if you keep this material in the daytime, it can potentially cool the surface. Why? Because it is not absorbing the solar radiation, so that it will not contribute to the heating of the surface. Okay, rather than to heating of the surface, if the sky is clear and dry, is the heat to the sky, which is at lower temperature, so that you can easily get the cooling. Okay. So now, okay, we have told that yes, there is a potential, or this physics works, and but whether India has the potential for the radiative cooling, and yes, what may be the potential, like in the case of MNRE publishing the solar energy potential, like 5 kilowatt hour per day, meter square per day, 8 kilowatt hour per meter square per day, 2 kilowatt hour per meter square per day, depending upon the locations. So we also wanted to know whether that cooling potential is also be there for India, because India has a very diverse climatic conditions. So we wanted to find that and plot what may be the potential for India for the radiative cooling. Here we can say that this is the energy balance which I have told previously. So you can see that there will be some amount of radiation which will be emitted from the sky, emitted from the surface, which is being transmitted to the sky. Okay, this is the radiation which will be emitted from the surface to the sky. This is the PS. That is the okay. Now, what are heat be added to this object or to the surface? Solar radiation will be coming in, and there will be heat which will be coming from the atmosphere also, right? Because the atmosphere is also at higher temperature, so it will also emit some amount of radiation, and the atmosphere contains the water vapor, carbon dioxide, and if the carbon dioxide and water vapor content is more, that have the potential to trap the heat, and that contribute to heating of the surface. Okay, and there is a contribution of non-radiative heat transfer, that is only by convection. Why there is a convection? Because the surface will be open, or it will be exposed to the ambient, and the ambient temperature will be higher than the surface. So if the ambient temperature is higher, then more amount of non-radiative heat losses, that is Q equal to HA delta T. Okay, delta T is the T surface minus of free stream temperature or the ambient temperature. Now, if say in the case of summer, okay, take an example of summer, solar radiation will be more, okay, humidity will be more, non-radiative heat flux will also be more. Okay, so that will the surface to the sky. Okay, so in that case, during the summers, the radiative cooling potential will be definitely be lower when compared to the winter season. Okay, winter season means not the rainy season or the monsoon season. I am talking about only the winter season. Now, what happens in the night? Of the solar, yes. So this contribution will be minimum. Atmosphere temperature will also be slightly lower when compared to the daytime, and atmospheric emissivity may be also be lower. So in the night time, the cooling potential will be higher than the daytime. Okay, it is obvious. Now, this is one like we should have a reflective coating from radiation will be to be absorbed by this surface. So mostly this should be a highly reflective surface or a white surface, so that it should reflect the radiation back to the visible radiation. Visible radiation should be reflected. Any doubt in this? Okay, now what we will do, we will evaluate what is this atmospheric emissivity, what is the solar radiation, and this non-solar radiation, non-radiative heat flux.
Excuse me, sir.
We will compute this. Yeah, please.
Sir, I just have a little doubt here. Can you just explain me here, like temperature difference between the sky temperature and ambient temperature, like how it is working here also, how is it working in the cooling potential? So just explain in this potential equation, please?
Okay. Yeah. The sky lower. Okay. The temperature.
Yes, sir. Yes, sir.
PS can be written as integration of Planck's law
Okay.
with the emissivity as well as the direction as well as for the
Mhm.
different wavelength. Okay.
Yes.
So like the more readings about that, you can refer to this paper. Actually, it is one of the published paper only by our group.
Okay, sir.
We
Okay.
have
Okay.
clearly explained about that equations. It was mentioned there in that paper. I think I have not mentioned that here. Yeah, I have not mentioned that here. Okay, but
Okay,
that
I
is
will go through
available
it,
in
sir.
the
I will definitely. Yes. Sir. Okay, sir.
and the
Thank you.
sky temperature is lower than atmospheric
Mhm.
temperature, and atmospheric temperature will be higher than the surface temperature.
Yes.
From this surface to this T sky, there will be some amount of radiation exchange.
Yes.
Okay, and from T atmosphere, which is higher than this T surface, will be radiating some amount of heat from the atmosphere to the T surface. So that is why here it is in negative. So the direction from
Okay.
heat transfer is atmospheric to the surface. And radiation from the sun, which will also be coming to the surface. So it is negative. Non-radiative will also try to heat the surface. So it is also negative. So we wanted to maximize this PS. How we can maximize this PS? Based on the surface emissivity. Okay.
Okay. Okay.
So the peak cool will be, or the how the cooling effect will be
Excuse me,
getting.
sir.
Yeah. Go ahead. Yeah, please.
What about the thickness?
Thickness of the.
Can you hear me?
Yeah. I can hear you. What about the thickness
Material.
of? No, it is a paint. It is a kind of a paint.
Thickness of that material.
It is a paint. Okay. It can be of micrometer thick. Doesn't matter.
Oh, it's okay. Okay, sir. Okay, sir. Okay, sir.
And like say, there are different materials which have different spectral emissivities. So like there is a we can classify, or we can broadly classify into ideal broadband, ideal selective, semi-ideal broadband, and semi-ideal selective. These are the actual materials which are available. Okay. So we can classify ideal broadband, ideal selective, semi-ideal broadband, semi-ideal selective. Meaning that ideal broadband means it will have very high emissivities from the 2.5 micrometer to 25 micrometer. Same ideal selective means it will have higher emissivities only in the 8 to 13 micrometer. Semi-ideal broadband means it will have lower emissivities, like not 1 but 0.93 assumed. These are assumptions, okay, from 2.5 to 25. And semi-ideal selective means it will have lesser emissivities but only in the atmospheric window. So these are the, so that based on these 4 conditions, this is only the emissivity of the surface. Okay, so based on these 4 conditions, we can evaluate what will be the cooling potential. Okay, so what we have done is we have collected the weather data, because the solar radiation is different region. Wind speed will be different for a different region. Yes, atmospheric emissivity is also be different for different region. So we have collected all this data, and then we have evaluated what will be the atmospheric emissivity. Then from the atmospheric emissivities, we calculated the radiative cooling potential for these 4 cases: ideal broadband, semi-ideal broadband, ideal selective, semi-ideal selective, and then plotted the radiative cooling potential map for India. This is also the published study from our group, research group. So we have collected data from around 498 locations of India at different states, and we have collected all this data, and then we have evaluated the radiative cooling potential throughout. Okay, then here I have this formula PS. Okay, what is the radiative cooling how exactly it is to be calculated. This is the emissivity of the surface, which will be lambda, and IB is the solar radiation. This is this sky temperature or the surface temperature, and this is again for the lambda, and it will also have angular dependencies as well as the spectral dependencies. Okay, so through this only we can calculate it. Okay, so we have written a Python program to calculate what may be the cooling potential and what may be the maximum cooling power, that is the cooling power, and what may be the lowest temperature which can reach. Okay, so here if plot for different surface temperature or the delta T, that is surface temperature minus the ambient temperature, this is for different months. Okay, then you can see that if the delta T is 0, then we can get the maximum cooling. Okay, if the delta T is 0, then we will be getting the maximum cooling, or if the cooling is 0, then we can say that we will be getting the minimum surface temperature, minimum possible temperature. Okay, so for 498 locations, we have come for 12 months. We have calculated all these things and we have collected this data. Okay, this is minimum possible surface temperature and what may be the maximum cooling potential we may have. And then we have used this data to plot the radiative cooling potential. Okay, so this one we can say that semi-ideal selective, which may be the representing the actual scenario. So we can see that even in that case, potential is there around 80 to 90 watt per meter square. That is may have for it for the India. Okay, it may be having higher potential in some regions and lower potential in some regions based on the atmospheric temperature and atmospheric conditions, and also based on the solar radiation incident on that region. Okay, this is the radiative cooling potential we have, and what. Okay, there are two things which are necessary: whether we have the cooling potential, and cooling potential without the required temperature, that is not a good place all right. So we wanted to be the minimum possible surface temperature too. So we can see that mostly 285 to 290 degrees Celsius we can easily get it in most of the locations, or in some locations we can get lower also, but we can say that 290 to 295 also available in at least 20 to 25% of for India. Okay. Meaning that this technique is not okay. Now, if it is not useful for refrigeration purposes, mostly, then where it can be used? It can be used for air conditioning purposes. And we are not saying that this will be a very good solution for air conditioning purposes too. But if this be combined with some vapor absorption systems, then that will enhance the or reduce the energy consumption of the conventional refrigeration systems. Okay, so in conclusion, radiative cooling potential is there, cooling is also there, temperature also it can go reach below ambient temperatures, but it cannot be useful for refrigeration purposes, but it can aid conventional refrigeration systems or conventional cooling systems to their energy efficiencies or to decrease systems. Okay, then what we have done is we have the potential. What are the applications we can study? Okay, whether we can go for water cooling systems. So we have done some simulations in COMSOL multiphysics on radiative water cooling systems also. Suppose say systems, we wanted to send some amount of water, hot water, and when it comes out of this radiative cooling systems, whether it will cool below the ambient temperatures or not. Okay, the same energy balances can be done here too, applied here too, and we have done it for different, for the same length of the pipe and with the different configurations of the pipe. So which configuration is better and which one will provide better cooling and all. I think this can be easily be done. And this is also one of our published research. And this is one of the research which we are doing it, building cooling with PCMs. So building cooling, can we apply this for building or space conditioning applications? So PCMs, people are already using it for space conditioning applications. But what happens if we coat this radiative cooling material above the phase change materials? Then what happens? So it can easily cool the, and also it can store the cooling, and which can be utilized during the nighttime period. Okay, so we have run 24-hour simulations. Then we have evaluated whether it is cooling, whether what is the solar temperatures and what may be the temperatures with PCMs and without PCMs, and with PCMs with the different thickness of the PCMs, what may be the liquid fraction, so how much amount of energy which is being stored. So these are some of which are presently we are doing it, and these are some of the unpublished results which I have shown here. We will be communicating these results soon to the journal, but nevertheless, we can see that it has very good amount of potential, and which can lower the energy consumption also. Okay, and I'll be presenting some of the case studies which are being experimented by some of the which are we are in collaborating with. So this one for building cooling applications. So what they have done here is they have cooled, or they have coated the building with radiative cooling material and without the radiative cooling material, and what may be the, and they have evaluated what is the temperature inside and what may be the cooling potential, or like what may be the energy consumption, difference in the energy consumption patterns. Okay, you can see that without RCC, the temperature was much higher, but with the radiative cooling coating, you can see that the indoor temperature and the rooftop inside temperature, that will be lower when compared with here. Okay, here you can see that rooftop inside that have temperature of approximately 5 degrees higher than the indoor temperature. So what happens here, this 5-degree temperature, that will again, if you are in adding a fan or anything by convection, that will add to the cooling load or the cooling demand of the building. But what happens if you are putting a coating, that temperature difference is lower or being minimized, then it will contribute, or like to the it will not add any extra heat load to the building. Okay, so in that case, what may be the temperature they can maintain? There are different settings also, and they've done it with medium settings, that is 24.5 degrees Celsius or 25 degrees Celsius, and they have calculated the energy consumption also. So you can see that they have achieved the electricity consumption, or they reduced the electricity consumption by approximately 20%. Okay, so this is what the conclusion and what should be the takeaway point is. This technology may not be an alternative, but when it combined with some solution or conventional cooling systems, it will definitely going to reduce the demand. Yes, and also it will improve the energy efficiency. Okay, overall energy efficiencies. Okay, so what we can say is, like as per the India Cooling Action Plan, there is an objective that we wanted to reduce the energy consumption by certain %. So we can add this kind of technologies that will also contribute to the lesser, or like reduce the energy consumption also, and also improve the energy efficiency of other systems too. Okay, so the other case study, this is also done by some of our collaborator only. What they have done is, like the problem is, like during the hot climate, hot seasons, what happens? The soil will be dry, and the root temperature will be higher. So if the soil temperature is higher, then obviously that it is crops also. Okay, so in that case, what happens if you can cool the soil by covering a sheet of radiative cooling coated sheet. Okay, so that will reduce the soil temperature. So if it reduces the soil temperature, more amount of the moisture content will be there. So that will be absorbed by the plant, and that can grow healthy. And they have done this case studies also inside a poly house and outside the poly house. And they have compared, and they have told that, with radiative cooling, if the soil is covered with the radiative cooling covered sheet, that have reduced the soil temperature and given better yield when compared to the other systems too. Okay. So the case study 3, atmospheric water generation. Not from our collaborator, but yes, this is one of the potential area. Here you can say that this is happening during the daytime and this is happening during the nighttime. So here actually they have a solar absorber and sorbent that absorbs the moisture from the atmosphere, and we have a transparent solar transparent radiative cooler, not the solar reflective radiative cooler. It is a solar transparent radiative cooler. So it transfers the solar radiation below. So that will increase the temperature of the solar absorber, thereby trying to release some amount of water which is stored in the sorbent. So vapor desorption will happen here, and that vapor will go to the top. And since the radiative cooler, this coating is at lower temperature than the ambient, so the condensation will happen, and that condensate can be collected. This is happening during the daytime. And in nighttime, what happens? The moisture which is present in the atmospheric air direct with the surface, and that will get condensed, and you can collect the water vapor. And in the meantime, there will be, if some amount of water vapor is present in the air, that will be absorbed also by the sorbent. Okay. And whatever the water vapor which is absorbed, that can be dissolved in the morning. Okay, so it will work daytime and nighttime, and continuously we can generate water from the atmosphere. So these are some of the applications which I have listed, and there are many other applications too. But yes, I'll stop here. And I hope that I have introduced some concepts to you which may motivate you to do further research in this area. Or, like if you have any doubts or clarifications, can please always do contact me. And some of our published papers which I have already presented, and I'll be sharing this presentation to ma'am as well, and ma'am can share this to you guys. Yeah, that's all from my end. Thank you.
Okay.
And
Okay,
this is
now
my-
it's time for the interaction.
yeah, please.
So we have one question posted in the chat box. Sir.
1 minute. I'll take it. I'll stop share. There it is in the chat box. Yeah.
Yes, sir, in the chat box.
How can biomaterials be effective and integrated into radiative cooling frames for rooftop application for sustainable housing? What challenges need to be addressed in terms of durability? Yes, this is very important question actually. Yeah, we are not sure about the durability or the reliability of this coating. Yeah, it is not been studied yet. So since it is not a mature technology, so further research is definitely needed for finding the durability or reliability of this coating. Say for an example, if you are doing this, actually we have studied some simulations by using COMSOL multiphysics for transformer cooling applications, because transformers which will be always staying without the shades. Yeah, and always exposed to the sky. So can we coat these radiative cooling materials onto the transformers so that some amount of heat it can be transferred to the sky so that it can cool the transformers? Yes, there is a potential, but there is a problem too. Suppose say there are more amount of dust deposition. What may happen? We are not sure about it. Firstly, secondly, if we clean that, whether this will be washed away, may be possible. If there is a rain, what may happen to this? No answers. Okay, so I request some of the people who are working in this reliability of these coatings, can take up this as a challenge. They can also work on this kind of materials and contribute to the this field. And any other questions? No. Any other questions? Binu TV, please. Thank you, Joseph sir, for raising this question. Please ask. Unmute yourselves and please ask.
Participants, if you have any questions, you can ask now.
I think I have taken around 1.5 hours, so 90 minutes of your time. Thanks for sparing your 90 minutes, and thanks for patiently listening to this lecture. And sorry, I may be go ahead.
I want to ask a question.
I
I want to know that you have said that there is a application of soil cooling. What could be that?
Yes.
I am asking the question that, sir, what could be the application of soil cooling?
So that it will not heat the soil, so that moisture will be retained in the soil. So that will try to, helping the plant.
What could be the specific area where that could be used? Like any specific area or a place?
Polyhouse.
That could be
Polyhouses.
Yes.
Maybe you can find in some of our applications also, like in polyhouses, like they will be putting the sheets below. And they'll be putting some holes and they'll be putting the tomato or any other plants also. You can visit some of the polyhouses and you can find that too.
Thank you, sir.
And if possible, it can be used also with our building materials. Like soil can be
Definitely.
used like that, so that the radiative cooling can be like while using PCM. Otherwise, we can use this soils because it is available readily. So if somehow it's possible to cool it, so we can use as a material for strengthening the walls and also for the radiative cooling. So there will be no such a demand of the PCM and something like that. So I think it would be great if we can somehow modify our soils, or somehow we can just alter their properties so that it can be more and more radiatively cooled down.
Correct. Thanks, Vikas, for this suggestion.
Thank you, sir. Actually, sir, I was very. It was very. Yes. Thank you, sir. It was very engaging and very interesting, sir. I would like to contact with you after this talk also, because it's something which is very engaging for me and was very interesting for me. So I will definitely would like to work with you also. So hopefully I will mail you and we will contact you. Okay.
Definitely.
Thank you, sir.
Thank you.
Thank you, sir.
Okay, if there are no more questions, then we can wind up. So, on behalf of the Department of Chemical Engineering, I extend our deepest gratitude to Dr. Manikandan for delivering such an insightful and thought-provoking session on radiative cooling potential and its applications in India. The detailed exposition on the science behind radiative cooling was very much informative. Thank you for taking the time out of your busy schedule to be with us and share your expertise. Thank you, sir. I would also like to thank all the participants for your enthusiastic presence and engagement during the session. So with this, we are winding up today's session. Participants, the feedback for session 2 is posted in the chat box and also shared in the WhatsApp group. So please do complete that. And tomorrow, the third session will start at 6 p.m. So thank you all once again. Thank you, sir.
Thank you.
Ma'am, there is one small request. Ma'am, can you hear me?
Yes, sir. Yes.
Yes, ma'am. Actually, I didn't receive that mail. Actually, I just registered yesterday through the Atal portal, but I did not receive any mail or something participant number over there. But I got a link from one of my colleagues, so that's why I just joined this meeting. But can you just check it and just arrange the participant number so that I can also feedback it?
Okay, sir. Can you share your details to my WhatsApp number?
Okay, definitely, ma'am. Can you how can I get your number, ma'am? And the group, actually, I have someone has just joined me that
Are you
group
in the
also.
group, sir? Are you in the group, sir?
Yes, yes. I just joined in that group. One of my colleague has just joined me over there, so I can just message over there
so
also.
you have joined now. Okay. So I
Yes,
am
yes,
there in the
yes.
group, sir. I am putting all the messages, sir, in the group.
Okay, ma'am. I'll
Okay.
post my details over there. So please try to send me that mail so that I can get the
Okay.
participant number also.
So I'll check, sir. If it is possible, we'll be doing it. Okay. I don't know whether
Okay,
the
okay.
adult site is closed for registration.
Okay. Actually, I had done yesterday, day before yesterday, I think. Yeah,
Then it
because
will
at the
be
last
fine, sir.
moment, maybe
Then no problem.
day before yesterday. Day before yesterday,
Ah,
I have joined. One of my colleague also joined. He got the mail, but I did not get it. So somehow
received.
there.
Okay, we'll check, sir. Okay.
Yes. Okay, ma'am. Thank you.
Okay, thank you.
Ma'am, just I want to know whether there is any WhatsApp group for this.
Yes, sir. One WhatsApp group is there.
I don't get any notification in that group. I don't be in the member in that group. So is it okay that we'll having this through mail, or is it necessary to join that WhatsApp group?
So I'll be checking your name in the adult portal, sir, and I will be sending you an email regarding the WhatsApp link and all. Okay.
Okay. Okay.
Okay, thank you.
Thank you.
Thank you.